Hey everybody. So I want to start off this video by posing a super heady philosophical question that has been posed for thousands of years now, which is the universe probabilistic or is it deterministic overall? And then so your first question and like first line of defense to that might be like what exact relevance does that have to actual grounded discussions and uh, how exactly could we prove those things out and what would be the significance of that if we could prove those things out? And so to me, the what answer to all of those things is the same, which is that it determines like how things are naturally built overall, right? If AI as a field is dealing with intelligence on some level, like artificial intelligence, and then defining and trying to determine and understand what exactly intelligence is, then it matters how it's built, right? Is intelligence built off of probability or determinism? And then like that question matters a lot, right? If you actually break it down and you think about it. And then so from that level, from like that asking that philosophical question, I've been asking myself kind of like that, like literal philosophical question for a few years now. And then so at this point, I've very clearly framed it in my mind that intelligence in and of itself is probabilistic. Can I make that and like that leap to say that the universe is probabilistic from there? No, but like I can definitively, at least definitively enough for me, outline and prove that intelligence is based off of probabilistic means and not deterministic means. And then so what does that mean? That's very important to the mathematics behind it. Like, and like, I think like that aspect of AI overall tends to like bother a subsegment of people within AI, right? Because there's a like you want the models to be deterministic and 100% deterministic, basically overall, right? And then so within that, like the bottom line is that you'll never be able to get a model that exhibits intelligence on any level as long as it's deterministic. And that's kind of what has been being proven out more and more and more. So within that, let's dive into this particular research paper here, which is an analytic theory of creativity and convolutional diffusion models. And it's put out by on June 5th, 2025, and then put out by Stanford University, and then as well as like a huge conference here. And then so within this particular research paper overall, this paper focuses on diffusion models, but to me, like the logic and exactly what they prove out here is you can take it and apply it to other like anything that involves deep learning architectures will apply to this framework to me overall. But so kind of what their overall argument is very simplistic, and then they prove it out mathematically, which is that so diffusion models essentially operate off of like the taking a step back. Their first they claim within this, and their argument is that diffusion models exhibit characteristics that are outside of memorization, but the internal workings and math as they're understood could be the outputs defy what we know about the current math. So how does that jive is basically kind of what they're breaking down within this. And then so what they dive into within that is very specifically that so the model goes for and tries to compute an ideal score, right? And then so an ideal score, let's say of an image, right? And then let's break that image down to a score. So if you can 100% replicate that image 100% flawlessly, that would be a score of 1.0 on our scale. Right. And then anything at less would be like 9.9, or if it's like, 0.5, 0.3, etc. And then so a 1.0 would be a perfect score on the scale. The bottom line that they point out within this research paper, and they prove out with all of this math that you see here, is the fact that it's physically impossible it's physically impossible for the models to actually achieve this perfect score. And then two, if the models were able to achieve this perfect score, it would just be flat out memorization. And then essentially the model doesn't learn anything in regards towards the like underlying mechanisms, the underlying mechanics, underlying patterns, because it just learns how to 100% deterministically do whatever it's assigned to do, right? Replicate this image like to 100%. Is our like the definition that we're using here when it comes to diffusion models overall. But again, like to me, again, this framework has been proven out with regards towards every single framework when it comes to deep learning frameworks, because you have overfitting within LLM models, which is this same exact phenomenon, right? Overfitting means the model just begins to memorize the patterns and the equations within this. And then so what they dive deep into very specifically within this is that like it's actually like built into how the models work and operate, and it's essentially their creativity mechanism that they don't actually achieve a perfect 1.0 score, right? That the fact that they're not actually achieving perfection, that there is dilutions, evolutions, convolutions, whatever like term you want to use within that, is like what actually leads to the creative process within these things. And then so to me, like tying this into further things, like so I have like several different architectures and models and frameworks that I've gone over and I've put out on this channel, and one of them is ghost memory, right? And then the concept of that is very simplistically that model memory and like for the models shouldn't be deterministic, simply because of the fact that human memory isn't 100% deterministic, right? I think that like to me, let's assume that like if we're doing this, from a pure scientific perspective, all we can go off of is what we know versus what we don't know, right? And then so what we know is that human memory is probabilistic. And then so the next question from that is there an advantage to memory being probabilistic versus deterministic? And then given those two outcomes with no other information, we don't know, right? We don't know if it is advantageous, but what we do know is that humans possess one of these, which is that that it's not deterministic and it's probabilistic. And then so within that, the question and it becomes we can go more into that direction, right? If we have to choose between those two, we have at least some sort of data on this side that says like existing what we know about the existing universe points towards probabilistic memory, and then what we're seeing more and more broken down within this is that probability being built into the equation overall is like what makes these models go, right? And then that's kind of like the bottom line that I want to point out within this. Like, I don't think that these models will ever be like 100%. Like, I don't think you'll ever have a benchmark across the board where these agents are scoring like 100% on any test across the board, like especially with like agentic activities, et cetera, right? And then I've gone into that a lot on different areas on my channel. But regardless of the architecture that you're utilizing, no matter what you do, et cetera, it's just, and this what this paper proves out, right? Mathematically, that would be impossible to achieve. And then like, the last thing I want to touch on related to this research paper is the concept around that, right? I think like not enough people take the next step from there. Okay, so it is mathematically proven, and you cannot argue it basically like, on any level, that these models will never achieve 100% accuracy, which means that there's going to be an error rate. And then so the next logical question that you need to ask yourself, because someone's going to ask it eventually, is who is responsible for that error rate? Depending on whatever you're implementing, right? There's going to be an error rate within that. And then so are you going to be legally liable for it? Like there's a lot of reasons beyond just like philosophical foo-foo why you should be asking that next question. And I don't see enough people at all asking that next question within this, right? And then like to me, like it's so what this, I mean, if I'm breaking this down very honestly and very simplistically within this, what this research boils down to and points out too is the fact that like it's a I mean, bottom line, kind of like a release of liability overall for the creators and trainers of these models, like flat out. That's exactly what this research paper is and does, right? Because it says that they do create a model, a diffusion model. There's been a question, like the legal question of like whether or not diffusion models inherently are like the same as like a transformer-based model and legally immune from like a lot of the like pressures that other models face within this, and then this paper definitively is on the stance like the defense could like 1 bajillion% utilize every single aspect of this paper to prove their argument that these models are producing novel definitions. But then the secondary thing that this thing would carve out from a legal standpoint and from that perspective is that like 100% when you're deploying and employing these models in an actual environment, you know mathematically that there's going to be some sort of error, right? Some sort of liability that needs to be taken into account. So then who is taking on that liability? And then ignorance of that liability isn't like a defense under any part of the law whatsoever, right? And then the law is very clearly going to carve that out because it's within this, right? Like it's that's what this paper is. The overarching argument within this paper is that the models are inherently flawed, but it's also because of the fact that these models are inherently flawed is what actually allows them to exhibit the characteristics that we label as intelligence, whether or not you want to actually like label that as intelligence or whatever label you want to put on it. If you want to, like you're on the council, but you're not Jedi, whatever, however you want to frame that is up to you from there. But whatever you're calling that only exists with probability within the models overall. It's kind of like the bottom line within this. And then I like this paper overall because it's again, there's no denying the mathematics within this. And then their argument is like so how they do this and they're able to prove this out mathematically is they take a diffusion model, they strip out the attention mechanism, and then they essentially follow and then see exactly how it denoises, how it's operating, etc. And then they show that from that base architecture that there's a bias that is inherent within the model, and then that model bias is what mathematically means that it will never get to that 1.0 on the scale. And then they just prove that out mathematically, right? And then so proving things out on a mathematical level is always the end road when it comes to these things. And then it kind of just kills all debate from there. So that's why I like diving into the research papers on this particular level. But so I'll leave a link here to this particular research paper, an analytic theory of creativity in convolutional diffusion models. And if you like this type of content overall, please like and subscribe. Thank you very much.